Hi and welcome back. Previously we have talked about the linear regression and how you can implement it in PyTorch. In this tutorial we are going to talk about computational graphs and the autograd system in PyTorch. Why do we need this? In deep learning related applications we have to calculate gradients in order to optimize our parameters. And for that purpose we have computational graphs, and the autograd system is designed particularly for this purpose, for calculating gradients. Before we start, we will import first the necessary libraries. So we will import NumPy as well as matplotlib, and we will also import Torch. Before we start, let's look at a simple example of how we can calculate the gradients or derivatives. We have x and y here. X will be equal to 3 and the y value is 3x squared plus 4x plus 2. Here x is a independent variable while y is a dependent variable. It depends on the value of x. This here is the computational graph of this equation. We can see that by going from left to right, we will replicate this equation. So 3x squared is this part, 4x is this part, and plus 2 is this part here. So if we switch x to be 3, we get 3 squared is 9, times 3 is 27. 3 times 4 is 12, and we add all of these values, so 27 plus 12 is 39, plus 2 is 41. So we get a value for y that is 41. Let's now see how we can do this in Python. We will first define x as a tensor, so torch.tensor of 3, and we will set the requires grad option to be true. This will automatically compute the gradients for us. We will set y to be 3 times the x squared plus 4 times x plus 2. So dy should be 41, so we can print it out. And we can see that y is equal to 41. Now we want to calculate the derivative of y with respect to x. If we know the derivation rules, we know that this can be rewritten as 2 times 3x plus 4, which is then equal to 6x plus 4. If we know that x is equal to 3, we can just plug it in and we get 18 plus 4, which is equal to 22. We will check how we can do this in PyTorch. In order to calculate the gradients, we will just use a neat function called .backward on the variable y. And this will calculate the derivative of y with respect to x. And because we have specified that x has a parameter requires grad that is equal to true, the gradient will be stored in x.grad. So we will just print out x.grad. And this should do the same thing that we did here, which is really useful. So we should get a value of 22, which is correct. Now you may be wondering, can we turn the gradient calculations off? Let's look at an example. We will define x as a tensor with a value of 3, and we will set the requires grad to be true. How can we look at this x? So x is a object or a tensor that has a certain value, in this example 3, and if we pass in the requires grad equal to true, it will do the automatic computation of the gradients, and the gradients will be stored in a attribute x.grad. So if we print out x, we can see that it is a tensor with value of 3 and it has the option requires grad set to true. So what if we want to turn this x to be a constant without the gradients? There are several ways, but we will explain two of them, which are the most used. So we will set x is equal to x dot requires grad underscore, and we will pass in the brackets false. And if we print x, we can see that it is just a tensor of value 3, so it is a constant without the gradient calculations. And there is another way, so we will just do x is equal to x dot detach. So this will detach all the gradients and turn the gradient calculation off, and if we print it out, we will get a scalar value. So this is a constant value 3. One very useful function in PyTorch that you need to be familiar with is the grad.0 function. We have mentioned that there is a forward pass and a backward pass, and the gradient calculation happens in the backward pass. One interesting thing about PyTorch is that when we optimize some parameter using a gradient, that gradient is still stored and not reset. What happens is when we calculate the gradient the second time, they will accumulate or add up. So the previously calculated gradient and the newly calculated gradient will add up and they will accumulate. The best way to understand this is by looking at an example. So we'll create a variable x, which will be a tensor of the value 3, and we'll set the requires grad option to be true. Then we'll create a for loop, so for epoch in range, and for example we will iterate 3 times. And we will calculate the y. Y will be the same as the equation before, so 3 times x squared plus 4 times x plus 2. And we will simply do the backward propagation. The gradient is stored in x.grad and we'll print it out. We can agree that the gradient should be constant, and we have calculated it before and it is 22. Because the x value is 3 and it is not changing. So let's print it out. We can see that the first gradient was 22, but in the second iteration it was 44, which is 2 times bigger than the first one. And in the third iteration it was 66, which is 3 times bigger than the first one. Why is this? This is the accumulation effect. The gradients are adding up, they are not resetting. A way to reset them is by calling the function we mentioned, so we'll call x.grad.0. If we print it out now, we can see that in the first iteration it was 22, the second one also, and in the third one also 22, which is correct. Now we talk about the so-called chain rule. What exactly is the chain rule? We sometimes get a more complex equation that has 2 or more functions. If we look at this example, we have 2 functions. We have a function g and a function f. We pass our x into g and get an output that we pass into the function f. And our final output is f of g of x. Now, if we want to calculate the gradient of the function f, of the output of the function f, with respect to x, we cannot just leap over this function g. Instead, we will go back until we hit x and we will calculate the local gradient of the function f, and then we will calculate the local gradient of the function g, which is the derivative of g with respect to x. And the local gradient for f is the derivative of f with respect to the function g. And at the end we will just add these two, or we will multiply them. And this way we will get the gradient d of f of g of x with respect to x. And that is how we can calculate the chain rule. Now we'll see a bit more complex example of how we can calculate the derivative. We have 2 variables, we have x and y. X is equal to 2 and y is equal to 4. We also have a function z, which is equal to x times y. And we get a value of 8 for this example. We have chosen a number for the derivative of the loss with respect to z to be 1. So we have hence chosen this number. How can we calculate the derivative of the loss with respect to each of these parameters? Well, we cannot just jump over this function as mentioned earlier. We first need to calculate the derivative of the function z with respect to each parameter. So to calculate the derivative of z, for example with respect to y, we first need to freeze the other parameter. So we will freeze x and we'll just calculate the derivative for y. The derivative of a variable is 1, so the derivative of y is 1, and we get x times 1, which is x. We will do the same for the x variable. So to calculate the derivative of z with respect to x, we will freeze the y variable, and the derivative of x is equal to 1. So 1 times y is equal to y. Now that we have these two values, we can calculate the derivative of L with respect to x. We will just multiply this value, so the derivative of L with respect to z, multiplied with the derivative of z with respect to x, which is this gradient here. And we replace the values, we set it to be 1 and 4, and we get the gradient of 4. We do the same for y, So we multiply this one with the gradient of z with respect to y, which is 2. And we get the values 4 and 2. Let's now see how the dot backward function really works in PyTorch. We will define a variable x that will be equal to torch.tensor, and we will create a tensor or vector of 3 numbers, 1, 2 and 3. And we will set the required grad to true. Normally, we would perform some operations on this x, so we will define a y that is equal to x times 2 plus 3, and another operation would be, for example, we will square the y variable. Now, if we print out z, we should get a vector of 3 numbers. These are the numbers, and to calculate the backward propagation, we would need a scalar, so we would do something like out is equal to z.mean, and get the mean value of these 3 values. And we would just perform out.backward. And now, if we print out, it is a single value or a scalar, and we got the x.grad values, the gradients, which are these values. Now comes the question, what if instead calculating the gradients for a mean value, we want to calculate the gradient for these 3 values? Well, in that case, the backward function has a very useful functionality. The current default parameter for the backward function is a tensor of only one value. That value is 1. This represents that it is only accepting one value or one scalar as input. How do we tell the backward function to accept more than one scalar? In this case, our z has 3 values, so in here we will pass in 2 more ones, and we will name this tensor v. Now, by calling z.backward and passing in that variable v, we have told the backward function that it needs to calculate the gradients based on these 3 values. So, by resetting this, we will reset the gradients, and we will just do the backward propagation. And now, by printing out x.grad, we can see the gradients for x. But in this case, these numbers are not the same as these numbers here. That is because we need to divide them with the total number of the values in x. So that is by 3. And we can see that we get the same gradients we got here. And that would be it for this video. This was just the first part. In the second part, we will see how we can optimize parameters using Excel and Python as well. If you want to read more about how the computational graphs and the autograd system work, I will leave the link down below for our blog. Thank you for watching, and if you like this video, drop a like and subscribe to our channel. Be safe.